Hi and welcome to the Neil Ashton podcast. In each episode, we explain some of the fascinating ways that science and engineering are changing the world around us. We talk to leading engineers from elite level sports like cycling and Formula One, to some of the world's top academics to understand how fluid dynamics, machine learning, supercomputing are bringing in a new era of discovery. We also hear some of their life stories, their career advice, and lessons they've learned on the way that I hope will be helpful to you too. So sit back and enjoy this episode. Hi and welcome back to the Neil Ashton podcast. So today's episode's just me, and I wanted to go through what I thought were 5 of the top important trends in CFD, let's say over the next 5 or so years. I'd love to know whether you agree with what I'm going to say. These are sort of more, I guess, high-level trends rather than getting into the specific details. Very happy to do an episode diving a bit deeper into one of these, but I thought I would maybe stimulate some discussion and get you thinking about some of these. And I have to also give a bit of I think that I'm coming from a certain angle here. I guess my experiences in everything I've done will bias me, and I just want to admit that bias. I come more from an external aerodynamics background in terms of CFD. I currently work for a cloud computing company. I'm obviously going to see things through the conversations I have and the lens I see. But I'd like to think that I see enough of what's going on in different sort of verticals and different areas that gives me a reasonable understanding of what's going on. So yeah, let's see if you agree. So yeah, 5 things that I think are important for CFD over the next 5 years or so. Not necessarily in chronological or like in an important order, but number 1 for me is GPUs and ARM-based processors. Why do I say this? It was the case when let's say back in 2013 or something like that, I remember going to a PAR CFD conference. So they still run parallel CFD. It's a great conference to go to sort of that blend between high performance computing and CFD. And I remember there like 10 years ago, this was at Barcelona Supercomputing Center, really great venue right on the Ramblas sort of strip. Anyone who's listening who went there will know it was a great conference organized by the Barcelona people. And I remember seeing presentations showing about GPUs, and I can't believe that was like 10 years ago now. And there was a real sense in the room of, I remember someone said, that you can only get good performance out of it if you write the code from scratch. I remember someone saying that, and there being a bit of a debate. And I remember there being sort of sensational claims that GPUs are this much faster, and a little bit of a ignore them sort of thing. And obviously at that time, NVIDIA was doing a lot of work to invest in CUDA and sort of giving funding to research groups. And I remember seeing this, and yeah, it registered on my radar, but a lot of people were debating whether it could be possible, whether there'd be enough memory on the GPUs. Was it really possible to rewrite a code? People said they have millions of lines of code. I'm never going to be able to do this. Fast forward to now, and I would say for me, it's incredibly clear that GPUs are going to be the dominant computing platform for CFD. But as I'll say later, things move very slowly, especially in industrial CFD, and so the adoption is going to take time. But I have seen enough to make me believe that, and I'll give for several reasons. 1, there are publications out there that show it. I've certainly showed it in public settings, and it's the ISVs and software companies have done it. And in fact, just for Auto CFD, this automotive workshop that I created back in 2018 and 19 with Gary Page, Loughborough, and now it's in its 4th edition. I think the slides are now up and the videos on the website. So if you go to autocfd.org and you scroll down and you go to the HPC presentation, Herbert Owen from Barcelona Supercomputing Center did a great job of taking everybody's submissions from CPUs and GPUs and then looking at what type of GPU, what type of CPU, and doing a really good job of looking at several different metrics. So the speed, per degree of freedom, per time step, looking at the cost. So we took a sort of a notional cost from AWS. It could have been any cloud provider. It's just, it's the only way of getting an actual price for these things, because obviously the cloud gives you the all-in cost. Whereas if you were to find a website that would give you just the sort of the GPU or the CPU, that wouldn't be the actual entire cost, including the power and the network, etc. And what it showed is that for external aerodynamics of cars, GPUs were more cost effective, at least 2, 3, 5, 10, it depended on the code, or even more, cheaper than an equivalent CPU at the scale that it was being run for a realistic problem, not a sort of toy benchmark problem. And they were faster, but that's a slightly harder one because it depends what the parallel scaling of the code is and how many CPUs or GPUs do you throw at it. Whereas the cost, obviously it's going to change a little bit on linear regime. If you're really badly scaling, the cost is going to go up relative. But essentially what it showed was the cost. Now, I have repeated this same thing myself personally with startup codes and ISV codes, and I have seen the same thing, which means that for a certain classification of workloads, and I can only speak what I've seen and personally, so I'll speak more, let's say, in plane design, car design, but I've seen it, and I believe it to be so in other areas. You're ultimately going to run your simulation cheaper on a GPU than a CPU. So forget about speed. It's going to be cheaper. And why is it cheaper? Ultimately, these are things like power efficiency, energy efficiency. So even though the GPU looks more expensive to buy for one node, when you actually work out how long does that node need to run for, it's easier, like I said, to calculate with cloud because you pay-as-you-go pricing. It is cheaper. And as soon as something is cheaper, economically, it makes sense. It is going to gain widespread industrial adoption. Now, where's the nuance to this is what GPU? There is in some ways a divergence. Well, not divergence, but there is a market for machine learning GPUs with a particular focus on certain precision, lower precision ultimately than what most CFD codes would need. And so you're going, from A100s to H100s, H200s, etc. to Blackwell. That are driving up, more and more performance. And CFD absolutely can take advantage of that performance. And it's great because we can jump on the bandwagon essentially of machine learning. But there is also another classification of cards that quite often are more designed for inference, but these sort of L40S, RTX type cards that actually have a very, very good price performance. So their raw performance may not be as high as those sort of more top-end GPUs, but for CFD, they actually are often, when you do the maths, even better price performance, and that's what we showed at this auto CFD. Now, the reason I'm saying that I think the GPUs will become the main is because if you look at the trajectory of GPU development in terms of generation after generation improvement, and you look at the same on the CPU front, I think it's hard to deny that, again, because of the investment from machine learning, there is a much greater boost in performance from generation to generation on GPUs than there is on the x86 CPUs. And the fact that there is rising competition now between NVIDIA and AMD, and also maybe there's room for more, startup or emergent technologies, that's only going to drive more and more focus. Now, I say ARM64 as well, because that has emerged as at first maybe more of a niche architecture that was harder to get people to convince, And I know, speaking from being at AWS, we have our Graviton ones, and we struggled for people to think, well, why should I bother to port my code, to ARM? But now, with more and more companies, with the other hyperscalers also releasing, obviously with NVIDIA, with the Grace system, sort of linking the two, there is far more, and there's far more reason for a major code to port to it. And as soon as that happens, the ecosystem jumps behind it. And again, the power efficiency and the performance numbers make it extremely attractive. That's not to say that people aren't going to be running on, AMD or Intel CPUs, of course. And as I said, the CFD market and engineering in general, or any use of CFD, tends to be slow. And so if from 2013 to now, there's been that sort of movement, it's not going to happen overnight. But what I can see is every single one of the major ISVs has or is porting their codes. The issue is that not all the features in the codes are available. So some of the multi-physics, some of the options are not yet done. So you may not be able to use the GPU version today because it may not have the feature that you need if you're doing some more sophisticated modeling, but it's probably on the roadmap. And more importantly is the codes, and these are more the startups like Luminary or Volcano or Flex Compute, and there are others, who have really focused on a GPU native code. And in the case of, for example, Volcano, taking advantage of GPUs, like designing it for GPUs, Cartesian methods, immerse boundary, etc. And there are others as well doing this, and hiring super talented people who have come out of universities and institutes with a deep, deep understanding of how GPUs work, programming it from the base, from the beginning, with the latest, programming languages and knowledge of how to extract the maximum performance, is really only going to accelerate it further. And I'll talk about this in the last point. This emergence of new startup codes is also invigorating, because simply, if you look through the eyes of a commercial company, why change? If you are the main company, main ISV provider, why would you change? You're earning good money from your licenses. You've got customers. And if your competitors are all basically doing the same thing, so none of them, let's say 5 years ago, 6 years ago, okay, none of them are moving to GPUs. Well, why should we spend all the effort doing it? Is it really that important? Is it really going to make a difference? Are we going to lose customers from it? And of course, the technical reasons, was there enough memory? Is there enough performance to gain from it? The one thing that drives a company to change is competition. And so with the emergence of alternative providers, many of who are specifically marketing their code around being GPU performance, it forces companies to do it. And you've seen that with Ansys sort of rewriting their solver and showing very, very strong performance. And at the Auto CFD workshop, we saw pretty much all of the ISVs specifically focus on their GPU performance and their speed, which 3 years ago was not the case. So everything feels like the right momentum now. The tricky thing is the whole ecosystem needs to work. So are the third-party meshing tools going to work on GPUs? And I mention this because we get to another point, which is around the sort of high-performance computing, because obviously if you're going to procure a cluster, if one code works amazing on GPUs, but all the rest are on CPUs, you then need to figure out, well, what's my ratio of compute options to buy? And so this links into one of the third points later. The other reason for GPUs is national supercomputers. Okay, what do I mean by that? Well, if you are, let's say, in Spain, and you want to show to your government that you, as a country, are pushing the boundaries of science, of R&D, and you're attracting entrepreneurialism. supercomputing has traditionally been a great way. It's a sort of, a big lighthouse, and the US is a more obvious one for that, but I'll pick a country other than the US. Your supercomputer, obviously a lot of that is then based on its performance, and the top 500 list is often, the metric, like what is the total performance of the system, the sort of exaflop race to try and get an exascale computing. A lot of this has driven to GPUs because the total performance of the system is much higher for a given power output with GPUs. And arguably, it is also a newer technology, so more novelty, more differentiation, can enable better science because there's more, throughput can be produced. And secondly, even more importantly, is because of machine learning. Because machine learning is now being integrated and is a key research topic as well. And so if you're a national supercomputing center, you want to be able to do ML research and you want GPUs. What does that mean? It means that if you're an academic and you want access to these supercomputers to do your research, like people do in Spain, let's say, you will have to write your code to fit on the system. And so sure enough, that motivated researchers in Spain, and now let's broaden it to the UK, to the US, to port their code to GPUs, essentially so they can run on the systems that they need to. And so there's been a push and pull. There's been a push because they think it is the right architecture to deliver better performance, or maybe that's the pull, but there's also a push because the system they want to run on has GPUs. So I should say that has also been the drive towards GPUs. There is once a decision is made that the big supercomputers are going to have GPUs, you almost are then having to, I'll just port my code, to go to it. And so that's more the balance to the industrial side and the academic side, why both are now meeting. And again, remember, many of these startup codes emerged out of more academic or government work where they had moved to GPUs because, one, they're just more aware of the science. And I would say this is where companies like NVIDIA have also put a lot of groundwork in investing in helping people to understand CUDA and helping them to port their codes. And that has now moved through into the startup. And as I'll speak about later, almost inevitably, many of these startups are going to be acquired by the larger companies. So there's an interesting sort of ecosystem and flywheel effect. So the next one is on AI ML. And again, you're typically really for AI ML or you're really against it. This tends to be the case with any new technologies. The reason I'm more bullish on AML, and that's through my own personal experience. Actually, and this I would encourage anybody else on, looking at code, writing code, doing experiments, publishing, organizing, really trying to immerse themselves. And I would actually make it similar to the way that I saw GPUs back in, let's say, the 2010s, where again I saw a similar dynamic of some people really being against it and saying, it's just all hype, there's no way they're going to be able to do it, I'm not going to be able to port, it's not, the technology is not going to be there, to others who are like, it's just a matter of when. I see the AI in a similar way, but with some more nuances, which is what exactly can AI be used for within CFD? Well, the first point I would say is the commercial pull. And you may, if you come from a more pure background, you may hate this sort of speak, but this is just the way the world works. When the large ISV companies, many of them who have stakeholders or boards to please, people invest in their companies in the current climate because of perception of how much are they embracing and leading when it comes to innovation, particularly around AI. And so a major ISV has to show to their board and stakeholders and shareholders that they are fully embracing and are doing something about it. And I would say in some ways many of them have had to catch up. Now, I don't know the inner workings of the companies. Maybe they've had many proposals beforehand, but certainly I would say the whole ChatGPT moment has, caught some of them off guard and made them really have to double down and decide what to do and if they can release it. that means that there's a lot of sort of R&D and focus within these major CFD and CAE companies. But this has also fed a lot of the startup market. So for a similar reason that many of the startups, and there are many to list, the Navistos, the Physics X, Beyond Math. I'm probably going to insult people by not mentioning them. I can't think. I'll probably list them more out. Null Concept. Yeah, I can't remember. There's a load of them, so I'm sure I'm offending some of them. The point is that, or Keywood as well, and yeah, okay. I'll try and make sure I mention most of them so I don't offend people. They have got VC funding because a lot of the VCs are seeing, could this be the next big thing? And so there are, to my last count, at least 10 startups looking at doing AI/ML specifically for CFD, and quite often for things like I spoke about car design or plane design. The fact that they have a lot of money does not necessarily mean that it will turn into success, but it does show that there's a lot of concerted effort. And when there are hundreds of people or thousands of people collectively working on this, that often leads to advancement. And when I talk about advancement, I typically mean in terms of surrogate modeling. So what some people would call reduced order modeling, but obviously more sort of sophisticated version of that, where essentially, and this is why it's particularly interesting from an ISV or commercial point, where you may essentially not need the CFD solver during the solve step. So you train a model on some data, and then once you have the model, you do inference, and that's completely outside of the CFD code, which obviously is worrying for an ISV that thinks we could be losing some of our, potential license or revenue or customers because they could be trying to use this other tool that we don't have. So, and just speaking commercially now, that means those ISVs really need to figure out, is this an important technology that could transform? And if so, we either need to develop it ourselves or we need to go and buy a startup. And that's really the key thing that's driving a lot of these companies to then, have a look at these startups. Why economically does it work as well is because on the one hand, the end user, just as GPUs, so what's the reason for the end user to be interested in AI/ML? For GPUs, the main reason was lower cost computing and potentially faster computing. GPUs, if the pace continues, we're going to see potentially over the next 5 years, 5 to 10x speed up in stuff. So not only is it a lot faster, and I'll talk a minute about this leads to more like high-fidelity transient methods to become possible even in a day or less than a day. For AI/ML, it's that the inference can be both cheap and fast. And that is something that brings up a lot of potential for companies. So, for example, it means that real-time CFD has long been spoken about, and GPUs were sort of billed as potentially enabling real-time CFD if you go back 5-10 years ago. But I would argue that that's not really turned out to be the case because some problems are not, they can be parallel in space, but maybe not parallel in time. So it doesn't matter how much compute you throw at it. Sometimes it just takes a while, particularly for transient methods, which you may need to do for accuracy purposes. Okay, you could do maybe a RAND or lower fidelity, but truly real time, click of a button, instantly get the answer. You have to make so many accommodations on accuracy that it ends up really not being worth the sort of the balance. The AI/ML is the interesting bit because the inference itself could be real time, but you could spend a lot of money and compute and time on training a model based on high fidelity data that could, if the ML model is accurate enough, give you quite a good answer in real time. And so this opens up a lot of potential, particularly in bringing CFD closer to the designer, closer to digital twins, more into, like NVIDIA's doing with Omniverse, into a sort of virtual world where you could be simulating things almost in real time. The classic example is the car designer, who's not a CFD specialist, who wants to draw a car, click a button, see it, get a sense of what the drag is, and then continue iterating. Now, I should say this is not in the short term, or even probably the medium term, about replacing high fidelity CFD. But I do think it has a very potentially disruptive role in the lower fidelity conceptual design phases that could really be important. And so commercially, this could mean basically a key tool in the market. And this is driving a lot of startups because there is a sense that there could be acquisitions or mergers from some of the big ISVs, or they could simply become big codes. And the CA market is $5-10 billion at least, and growing. And it's growing because there is a desire for digital certification. There's a desire to go more into the virtual world because it's cheaper and faster than wind tunnel testing or physical testing. So now there is still, and I want to make this very clear in my mind, many challenges and many areas that will most likely change dramatically in this space. I do not believe that any of the current methods published today will be the method that we end up using in 5 years' time. I could be wrong, and maybe it'll only just be iterations of it, but the field is moving so quickly that I just find it hard to believe that what we have today is the best we can do, essentially. And I say this because if you look at the CFD world, actually a lot of the breakthroughs in terms of the physics or the modeling were sort of done 20 years ago. You know, most of the warm-up LES or hybrid RANS LES or RANS modeling is actually 20 years old. And what's the novel bit is more the computer science, the use of GPUs, etc. But the actual breakthrough modeling, mathematical modeling, was done 20, 30 years ago. There's obviously some new developments, but most people, if you're using DDS, you know, what's that, 2004 or something, depending on which version you're using of it. If you're using K-Omega, SST RANS, it's 1994, so what's that, 30 years ago? So it's a bit like going back to 1994, the K-Omega comes out, and it gives good results and thinking that's it. I think we're in a similar time with the AIML that, yes, there are many startups and companies, but I don't think the actual modeling or the accuracy today is anything like we'll see in the future. And so that means there could be a lot of change, a lot of disruption. And that's why I think it's a really important area to get into, because there's no doubt there has still been major issues improving scale. Can these AI methods, you know, work on hundreds of millions of cell meshes? Can they work in terms of the accuracy? You know, have they really shown how accurate they are down to, you know, a drag count difference? There's been a lot of studies, but there's been limited real concrete evidence of it away from just sort of marketing. And the big question, of course, is around foundational models. So most of what the startups and most people who talk about it are doing is saying, we'll take the data you have as company X, train a model, you train a model essentially, and then you do inference on it, as opposed to ChatGPT-like methods that take huge data from the internet, and now by paying providers, they train a model for, you know, months, and then all you're doing is using it as inference. They've done the training, and they're recouping the cost from that through a subscription model or pay-as-you-go through the inference. Whereas in CFD, we're basically saying you have to do the training with your own data. The future is, could there be a way of a company pre-training a model and then you just do inference? I will definitely do a more of a deep dive on this, and hopefully if you look in season 1, I've spoke to 3 or 4 top ML people that I think they largely agree that this is a super exciting space, but there's still many questions and uncertainties around including physics, not including physics. And I go back to the statement that I just don't think the methods out today are the ones that we will use. But the breakthrough moment could be any time. And that's why I think it's such a super exciting space. So the second one is AIML. And of course, why do I mention AIML? Because it's linked to the first. AIML needs GPUs. And as a company, if you're being asked to train ML models, then GPUs is the only way to do it. And therefore, it makes double the sense to procure a GPU type cluster or predominantly GPU cluster, because it can be used for your ML and your CFD. Now, the third one, which again, I believe, takes its evidence from these first two, is cloud computing or SaaS type products. And again, I have to be, honest. I'm clearly working for a cloud computing company, but my belief is independent of working for that company. And I think, and hopefully I can give some evidence to back that up. The reason I'm saying this is it is undeniably true that the hyperscalers have huge investments in compute and are able to give access to compute that most companies may not be able to get at the size that they want, and the frequency and the access and the variety. Now, there may be times when there's a mixture of the two, and again, it's an evolving thing. If you already have, a lot of on-prem work, then maybe the cloud for you is a sort of a burst option, or a backup option, or it could be a primary option. There's different models, and this will evolve over time. But the fact that major companies around the world are moving to the cloud, because the way they see it is less of a what's the cost of the compute, what's the cost of the hardware, but more what can people do with it. The point being is that there's a lot of the biggest misconception with the cloud is that it's just service to rent. That's maybe the way it was 10 years ago, but now there's so many high level services added by all the cloud providers that actually offering is not only to access the compute, but many services that makes it easier to do things, whether it's machine learning, whether it's high performance computing, or whether it's databases or virtual or end user computing, many things that makes it easier for your end users to do stuff, or for your sort of IT teams to do things that they would have to have spent more time doing. So it's making them more efficient. So often when people look at a sort of a cost thing, the cost only really works when you take the value of doing everything. And that's why many companies are driving this. And the reality of what I've seen, at least, is the top down is really pushing this. So the CIOs are driving this, and so it's becoming, a reality for many companies. But like 1 and 2, cloud for many companies is still a journey, and so they're not fully moving to it. But the reason it's appealing is because if you want to get access to quite a different number of GPUs, or you want to test out new GPUs, the reality is it's probably the easiest thing. If you want to go and test a GPU, it's probably easier just to, get an account on a cloud provider and do some testing. Now, of course, there are challenges sometimes with capacity and things like that, but that's more of a transient effect given still the things of COVID and supply chains. It makes sense to procure it through a cloud system, and you're seeing that, with most companies. Now, the reason I'm sort of linking that to the others is there was also a time when many of the ISVs and companies and startups said, oh, the cloud, it's just a fad. But now many of them have turned around because they see it as an easier way of delivering their software to you. And this is where the SaaS comes in, software as a service. Now, we're used to software as a service because many applications we use through an app. We just go to a website and we use it. That is software as a service. So, one option used to be that you would download and install something on your computer, or you can go on. So something like, Overleaf, I use for like writing papers. It's a web-based platform where you can write LaTeX documents and it's all stored there in the cloud. You don't have to download anything locally. Now, that makes it a much easier, nicer experience, and it gives access to everything without you having to have it. The analogy would be for the CFD side is the current way of doing it is you would take a piece of software, a binary, let's say, or open source, and you get the software from them, but you have to do all the hardware. So you would install it on your local computer, on your hardware. But then what if you want a bigger computer? What if you need more memory? Well, you'd have to go and buy a bigger computer. What if instead you could go through some website, access that same CFD software, or some, through website or application, and it sorted out the compute for you. So you just ran the simulation, and in the back end, it was provisioning a bigger GPU or a bigger CPU, depending on what you never needed to worry about that. That is the value of the SaaS. And it links to the cloud because they're all running on the cloud. So the cloud gives those companies the ability that they don't need to go and buy data centers. They don't need to go and manage compute. They can just pay a cloud provider. And so you are getting that, and they're using the cloud. And that's essentially how the two ways that we see, and I see, of using the cloud. You can either use the cloud, and it's essentially just a mechanism to get compute in a remote fashion, and you don't really notice it. You just SSH onto a machine. You don't know whether it's in your cloud account or whether it's in some physical data center that you own. And of course, you can use high-level services. And the advantage of that one is you keep everything, let's say, in your account. So you have an AWS account, all your data's in there, you're a big enterprise. But you have to know how to use AWS. You have to know how to do all the cloud. The alternative option is you just say, well, I want to use ISV software A. Let's just, for argument's sake, let's say, Star CCM has a SaaS, a version. You can just go in and then use that, or it could be any other ISV. I'm just using it as an example. You can go in and pick the platform that you want, the compute that you want, go in, and they provision it for you. And so you've not had to know any AWS knowledge to get access to that compute. That is going to become more and more the mechanism. You look at Luminary Cloud. Cloud is in the offering, right? They are a cloud-first provider of CFD with the exact thing I just said, that it makes it easier for you to run stuff without having to worry about the compute. There are many of like SimScale or Flex Compute, or there's more and more, whether it's a startup or an ISV, that are offering cloud-based backend, and that's why it can be, in my mind, a very positive thing, because it's also, let's say, forget about the commercial side. What if you're an academic code? If you want someone to use your code or to give access to it, actually might be great. If you build your own sort of SaaS platform, you can give people access to your code or collaborate, and it could be private, remember. It doesn't have to be fully public. You could just do it through a username, password, and they log on and you can collaborate. There are many sort of openings to this that haven't been fully realized. People can create codes and products and serve them to people without being a sort of delivering a CD to someone, that they have to install on the computer. The cloud, we use it every day. It is a way of delivering things to you, software to you, that CFD has to date not fully embraced, but that is something, a bit like GPUs and AML, which will only increase. And I personally think it's a good thing, and it's something that you can, explore yourself. As again, not saying that, people buying their own desktops or their own data centers is going to stop. Of course, it's going to continue. But I think the percentage, and the data shows us out, the growth of HPC for the cloud is something like 15% year over year, whereas HPC on-prem is like 8%. And I think that's Hyperion, third-party analyst. The data shows it is growing, and so in this episode, it's more making you aware of the trends. Whether you agree with them or not, it doesn't really matter. They are, in my opinion anyway, the trends that are emerging. Now, what do these three things mean? GPU, technology, AI, ML, cloud. In my mind, it means that companies can move to higher fidelity, transient methods, or if your use case doesn't still allow you to do, let's say, a scale resolving type simulation, it could just mean bigger meshes if it's still steady state. It could mean running the simulation for longer, converging it to even tighter tolerance. It could use more equations for your chemistry model, more physics in it. As soon as you have faster, more compute and access to more of it, let's say through a cloud-like platform, you are going to see more use of it. And why does this matter? Because ultimately it's about accuracy. The biggest problem for CFD and trust for CFD by very senior people in companies or by academic research is its accuracy compared to physical testing, right? That's always going to be the put down. The CFD looks good, but how accurate is it? Well, as we all know, accuracy is heavily linked to compute. And that's why I think this really will set up a new wave of move to digital certification. Digital certification, or certification by analysis, has long been a goal for aircraft and car companies and any industry. But I would argue that compute and the method you can use is a limiting factor. Well, once the compute starts to become relaxed, the methods, you can use better methods, which gives you more accuracy and gives you more evidence to do less physical testing, or even if you do the same physical testing, just more virtual testing. And that will deliver, in my opinion, return on investment, because companies can shorten that time to release a product, or science can be done at an even greater scale. So, DNS can be done at much better resolutions. Large eddy simulations can be done for more realistic problems. You can add more, multi-physics modeling inside cases because you have more compute. You can do multi-physics. So many more things. So I think whether it's more physics or just simply things like smaller time steps, larger meshes, all of this will mean more accuracy. And I really do think that that is going to drive greater use of CFD and CE. So I think those markets are only going to increase because of 1, 2, and 3. The adoption, this is not, in my opinion, a static. This is a growing and will continue to grow, because its value to a business will be beyond just pretty pictures and actually meaningful improvements in design and making things safer, hopefully. Safer, faster, better, the usual metrics. So what's my final fifth point to this? Is this means, in my mind, mergers and acquisitions, which is sort of interesting. And again, it's a slightly more commercial angle, but I think this is interesting for any people who are looking to find startups or people interested in the cyberspace. Whenever you have destructive technologies like this, whenever you have the option of new hardware, the emergence of AI/ML, the emergence of SaaS providing and the thing that has, and high-fidelity transit methods, it means it's perfect time for startups. And we are seeing the startups. Why now? In the past 2 years? Why didn't we see, Illumina, Cardo, Volcano, Flex Compute, etc. 5-7 years ago? Because I believe because of the GPU technology, because of the cloud, it's set the right environment. Why are we seeing 10 startups now with AI/ML methods? Well, part of it is the technology, but it's also the environment because of the huge Gen AI boom that's giving reason for these VCs to fund these sort of companies. Well, as soon as you have lots and lots of startups and lots of main players who own majority of the market, that means there's going to be mergers and acquisitions, for sure. The big companies will acquire the smaller companies to keep market. But there is always the potential for a disruptor, that a company does not just get bought out, but actually rises to really challenge these companies. I don't know which one it is, because to date, the large companies like Cadence and Synopsys, the big EDA companies, and if people don't know, EDA is probably even bigger market than the CAE. They bought in to those. So, Cadence have acquired a number of companies. Synopsys have acquired Ansys, and Ansys have acquired a number of companies. Siemens, obviously, Dassault. So you have these players who see the bigger picture, which is the digital certification, which is the digital twins, which is the way that it can really transform manufacturing and the engineering space. And for them, they see that simulation is a key bit of this. And this is really the sort of the big picture, that it's a fantastic time, in my opinion, to be in CFD and CE. It's a fantastic time because there is real value that can be created, and the dream of someone sat there and virtually designing something and testing it and seeing it in through some sort of virtual glasses, it seems to be on the horizon. So I think the next 5-10 years we'll see two things. One, people doing the same they've always done. That's the honest truth. It doesn't matter. There are some companies doing the same sort of modeling they did 10 years ago, and fine. If there is all this new technology, that's nice, but I'm just going to keep doing it the way I'm going to do it. For some, that will happen. But I think for others, there will be a dramatic change and acceleration. And I think this is only a good thing. So that was my 5 main trends. I would love to know whether you agree. It is totally just an opinion. I'm sure I've missed many things out, and I'm happy to go into more details on other things and be corrected if I was wrong in some. But I hope you found this interesting, and it's got some of your brain, thinking of, does this apply to me and my thing? Is this just a more niche thing to certain segments? But yeah, hope you enjoyed it. We've got some great guests coming up over the next couple of months, which I'm super excited by. So I don't really like to say this too much, but apparently it helps. So if you are watching this on YouTube, if you sort of like and subscribe, it helps the YouTube algorithms, and it also lets you know when there's something. But also if you're on Spotify or Apple, I think you can click one of the buttons to follow the podcast, so that when something new comes out, you'll get notified. All right, thanks very much. Hope you enjoyed it. See you soon.